Right, so we have now taken care of the theory behind our calculate desired position method. Now we just have to implement it. So Lee, take it away.
All right, we're back in TP Camera inside of Visual Studio 2010. We're going to start off by setting up our public float distance smooth. And I think I hit caps lock by accident. Distance smooth. And we're going to set this to be a default value of 0.05. Now we also need a velocity distance. So we're going to make this one private. It's also a float, and this is VEL distance.
Right. And that's that required portion of our smoothing.
And we're going to set it to be defaulted to 0F.
Okay.
All right, now we're going to scroll down and we're going to find our calculate desired position. Now we mentioned we also need an additional method, so I'm going to go ahead and skeleton in that as well. So this will be a void calculate position. And it actually isn't going to be a void because it needs to return a position. So that will be a vector 3 that it returns. And we need to take in 3 arguments. The arguments that we're going to take are going to be a float rotation x, a float rotation y, and a float distance. Go ahead and add our braces. Now let's go back to calculate desired position. We said we have to do 2 things. We have to evaluate our distance, figuring out our smoothing factor of it.
Evaluate distance based on that smooth calculation.
And then once we've got our distance, we need to get our desired position. So we'll figure out what, or calculate what our desired position is going to be.
Desired, past tense.
Yeah, that's it. And now that I think about it, there is actually one thing that actually, I'm wrong. I'm thinking ahead again.
Yeah, you are. I actually think I know where you were going.
I was thinking about position, but we don't need that until
you're in good shape.
Update position.
Yep, you're in great shape.
What we need to do is let's calculate our distance. So we know that we're saving our distance inside the field called distance, and we need to actually go ahead and smooth damp this. So we're going to call mathf method look for smooth damp, and we said we have to know 4 things for this to happen. We need to know our current position, or current point that we're going from and to the point we're going to. In this case, our distance is the point that we're at. We're going to our desired distance. We need to send it a reference to our velocity, which is VEL distance. And we have to give it our smooth time, which is distance smooth. So that is everything we actually need to calculate our smooth distance.
Okay.
So all that big long theory just boils down to a single line of code.
Single statement. That's right. That's how it tends to go, though.
So now to get the calculate our desired position, it's a similar principle. We're going to take our desired position, which we don't have. So we need to add a desired position because we need to save it.
Yeah, of course.
So let's go up to our fields. We'll add another private field. This one will be a float, or sorry, vector 3.
Right, because it is a position.
It is a 3-dimensional position. So this will be our desired position. And this is where we're going to save our desired position. I'm going to start it off by setting it to be a vector 3 zeroed out.
Okay.
So that gives us our desired position. So I can come back down to where we're calculating desired position. Say desired position is going to equal what we get back from calculate position, and we need to pass in the stuff that we said we need. Now, if you remember our discussion, we said we have to reverse our axes. So rotation X is actually going to be sent mouse Y. Rotation Y is going to take mouse X, and then we need to send our distance, and we'll just send it at the distance that we just calculated in the previous line. So we've evaluated distance, applied smoothing to it. We're using that to feed into our calculate position along with mouse Y, mouse X, and what we get back out will be our desired position.
Okay.
Now, to calculate position, we're going to go to where we skeletoned in calculate position, and we've got those 3 lines of code that we were talking about. The very first being creating a vector called direction. So we're going to make a new vector 3. We're going to call it direction, and that's going to equal a new vector 3, and we pass it 0 for the x value, 0 for the y value, and the negative of distance, because we want this vector to point behind our character. Next, we need to create our rotation. To do that, we need a quaternion. We're going to call it rotation, and we're going to create the quaternion by using the quaternion.Euler. It requires either a vector 3 or 3
individual floats.
So what we're going to pass in is rotation X, rotation Y, and 0, because we're not actually going to roll the camera.
Right.
Now we need to return our position. We've got everything we need to calculate it, so what we're going to do...
Just do the calculation.
Yep. We're going to hit return and do our calculation. We need to take our target, look at dot position, and because target look at is a transform, we can directly access its position. We need to add the result that we get by multiplying rotation by our direction, and that will return our desired position offset by our target position.
Okay.
That is everything that we need to do. So all that theory boiled down to 5 lines of code.
And we've discussed that up to this point. That's really what's going to happen. It takes a while to explain exactly what's going on under the hood, but really the code is very quick and simple. So that is everything that we needed to implement in this video. That's going to wrap things up. Thanks for watching.